welcome to a brief presentation I'm going to be doing about a couple of programming projects that I've been working on in relation to orbital propagation. Space system engineering is the type of work that I want to go into, and a lot of the requirements for that job come from understanding how objects and bodies move in space. So I've been working on a couple of projects over the last year, and I just want to briefly mention them and give some insight into what I've done with them, and also as a way of keeping myself accountable to see exactly what I'm working on, where I've come, and where I want to go, so that I can share the progress of all of this. So first off, this is the website that I've made just to show off all of my projects. I'm pretty proud of it, but that's an entire other topic. But what I have in here is my orbital simulation projects. So at the top here, this is my first project that I did in the fall of last year. This was back when I was first, coming off the trails of learning Java, with a bit of a short stint in pursuing a computer science minor. And I went ahead and wanted to work on a unrestrained three-body problem in Java. The issue with that is that it was a purely numerical method. It was entirely just based off of calculating the force between all the bodies and not even necessarily propagating, but just incrementing time and doing all of the real-time calculations for every body, for every frame. Pretty time-consuming, but also it was written in Java, which was the only main programming language that I knew at the time. I also knew C++, but I just took a class in Java, so that was my first instinct. And on the right here is a bit of a GIF that I made of just an original simulation. The red trail is the Earth relative to the blue point in the center that's a little bit harder to make out. It's supposed to be the sun. And then the green object is just a body that I arbitrarily made in a relatively elliptical orbit. And with that elliptical body, there was no real method to it, because there is no real knowledge of orbits at the time. I just created a body, and I gave everything a position vector and a velocity vector, and I just let it propagate itself. So there was no understanding of the equations behind orbital mechanics. It was just pure trial and error, which was not very efficient, but it was my first foray into the topic. More recently, this is the second project that I've been working on in Python, and this is something that I've actually just done this month, and that I've more or less called a wrap on, at least for the first section. So I just started to take a couple of classes. One is spaceflight mechanics, and the other is space systems, both of which revolve around, well, not necessarily revolve around, but they both touch on the topics of how orbits work, the different types of orbits, how they can be propagated through space and time, how transfer orbits work, all of that. And we were given some sets of equations that we can use to pretty accurately predict where celestial bodies will be, given some initial conditions. So what I did in this project, and that I'd like to show off, is a rewrite of the first program in Python using these principles, and how I've implemented it and how I want to improve it. So let's move on over to that. So here's just the README from the program. This is all available on my GitHub page, by the way, and that's available here just by following this link. It takes you to the repository with all of the files. So I'm actually going to close out of this README and just get into the meat and potatoes of the program. So the best place to start from this is from just the plain data. So what I originally wanted to do was try to find an API or something of the sort where I could pull live data in to use as an ephemeris to find all of the different bodies in the solar system, all of their, ideally just the apoapsis, the periapsis, and argument of periapsis at some epoch date. And I stumbled upon Spice, which is supposed to be a JPL backed source for this. And I spent a good couple of days trying to figure out how I could possibly use that repository. But then I ran into some issues with PySpice, which is the Python program that allows you to interact with Spice. Just some issues with parsing the data, parsing different files, getting the files, because apparently you can't just pull them directly from the internet. You need to download the data files, which is not ideal. So just to get the program up and running, basically what I did is I just scoured the internet and I just found some numbers and I just put it all into a Python dictionary, which I have in this file, celestialdata.py. And this is just purely for having it available in a file that can be easily modified for the time being. Ideally, I would like to have some kind of GUI and an API that will update this in real time. But for now, this is what I'm working with. So just quick crash course, pretty much almost all the planets, as well as Psyche, because that was pretty relevant for the time. And as well as something that I've been trying to work on for transfer orbits. And that's just kind of still very experimental. So this is the dictionary, and that feeds into this program, which is called config.py. What this does is that it takes that dictionary and it returns it returns another dictionary where any of the bodies mentioned in here are the ones that are taken in to these simulations. So say, for whatever reason, you're trying to do the simulation and you don't particularly care for Jupiter, you could simply just remove this from the entry and it will not be accounted for in the simulation. Just for the sake of consistency with the website, I'm going to remove the attempt of a transfer orbit here. Actually, sorry, I will not, because I'm still working on ironing all that out. But basically all this does is that this main function is called from the main Python file, and all it does is that it takes this list and it uses this function get celestial data to just take anything in the celestial data dictionary that matches those keys and puts it in another dictionary here, which is returned. So basically all it is doing is taking all this data, it's basically packaging it all nicely depending on what you specify here. This would be, if I wanted to make a graphical user interface, what could very easily be specified, and then that all feeds into the main simulation file. So obviously up at the top here we have the libraries that I'm using config, which is the config.py file for getting our dictionary. We have math, obviously, for trigonometric functions, and then the matplotlib library, which I'm using as a means of plotting all of this data and make some nice visualizations. And then here I'm just defining some global variables that I use in my simulations, and then defining the maximum and minimum values of the axes. These are currently set to 800 million kilometers, which I believe is just past the orbit of Jupiter, but I know it was in the simulation there. And then here we just have the definitions of some functions, and I'm actually going to skip down to where the actual code starts, and we can get to each function as they're called. So what it does initially is it basically sets the initial values for each celestial body. So what it does is that it iterates through everything in the list that's provided in the config file, which is your config list, and that is equal to config.main. So all that is doing is that's going in here, and it's taking all of the data from the celestial data dictionary and is putting it into this config list file, which is going to be a dictionary. And the reason why I'm primarily using dictionaries in Python is because they're one of the easiest ways to save space and time complexity, because all you're doing is you're just looking up a key, you get a value. It's easier than lists, it's easier than vectors, and I just find that's the easiest way for me to handle all this, especially because it's doing a lot of math, and I like to skip over that if I can. So it's iterating through each of those entries, so all of the user specified bodies. And the first thing it does is that it calculates the eccentricity of each orbit. So in the dictionary, each entry has an apoapsis radius and a periapsis radius. So in order for us to find our parameters of the orbit, one of the easiest ones, the two big ones that we need to find are eccentricity and semi-major axis, which can obviously be found by these two equations, apoapsis minus periapsis over apoapsis plus periapsis, and then apoapsis plus periapsis over 2 gives you your semi-major axis. And then next here for these bottom couple lines, what this is doing is just creating some initial variables in our dictionary that we're going to use later. So x vals and y vals are lists that will contain the x coordinates and y coordinates of each planet as it's being propagated through time. So in each iteration, it will append an x value and a y value to the specific list, and then that can be plotted using animation. It's also setting the initial time of each object to 0, the true anomaly of each orbit to 0, and it also calculates the period here, which is 2 pi times the square root of the semi-major axis cubed over the gravitational parameter of the parent body, which is the sun. So we have eccentricity, semi-major axis, and the period of all the orbits, as well as their true anomaly. So that sets us up to do some calculations to find whatever we want about the orbit, pretty much. The only thing that we could possibly need is angular momentum, but none of the equations that I'm using require it, so I just simply omit it. So the rest of the main function is super simple, but because it's iterative, it's going to get a little bit complex, so bear with me. So what we create next is the figure and axes for matplotlib, and this line is pretty straightforward. It's just create some subplot for the graph to reside in, and this function does all the magic. So it's an animation, function animation. This is from the matplotlib library, and it takes that figure that we just created, as well as the function animate, which will animate it, and this has a set number of frames. So I just set it to 100,000 just to run for a decent amount of time. And then this was initially set for a 1 second interval. I believe now it's set for 1 millisecond. So when this line of code is called, we'll go over to the animate function here. And what this does is that it takes everything in. So this takes in the config list as a global variable, and then new config list. So to update it is update data. So update data is another function. It's getting a little bit nested here, but bear with me. It's a lot of math. So first we declare our global variables, and then what we're doing here is we're iterating through every orbital body. We're updating everything. So obviously we have our orbital period, we have our delta t, which is our time step, and that's in relation to the period of the orbit, just so everything moves at its own speed. And then we have our mean anomaly. This is one of our first astrodynamic equations that we're going to use. And we have all of our different anomalies that we'll use to get from time to the true anomaly of the object along its orbit. So to go from time to theta means to convert theta to mean anomaly to eccentric, and then from eccentric to theta. So we have 2 pi t, which is our mean anomaly, and then we have our eccentric anomaly. anyone who might know the equation for this, it's that the mean anomaly is equal to E plus the eccentricity times the cosine of E, which has no analytical solution. So this requires us to do a numerical solution. And this is where things have to get a little bit creative. Because the issue with a function like this is that because your eccentricity is a function of mean anomaly and you have to do a numerical approximation, those will actually diverge for very large values of your mean anomaly, specifically anything above 2 pi. So what we have to do here, and a lot of this is just pure iteration, is that if it doesn't converge, then we just adjust the guess. So if, say, we, if we're not quite there, we improve our guess. So it's a very iterative process. But the magic really comes from this line of code here, which is basically, if your mean anomaly is too large, divide it by 2 pi and just use the remainder. So any additional orbits that you've completed, just take the fraction of an orbit and work with that. And I haven't had any kind of divergent issues using this to do any kind of numerical solving. So this, I don't know if there's any kind of more efficient way to do this in terms of time or space complexity, but this is the solution that I've come to. So we go back to this and we find our eccentric anomaly using that equation. And then what we do is to find our true anomaly in our orbit. There's a pretty long equation. I'm not going to pull up an equation sheet for it, but all you need to know is that rearranging it for theta, you have this mathematical equation, which is 2 times the inverse tan of the square root of 1 plus eccentricity over 1 minus eccentricity times the tangent of your eccentric anomaly over 2. This is just a bit of an algebraic reassembly of the main equation, which I believe is tangent of theta over 2 is equal to square root of yada yada. So it's just rearranging for theta. And then because we have theta, now we can solve for our radius in the orbit, which is our distance from the main focus of an ellipse to the body, which is equal to your semi major axis times 1 minus your eccentricity squared over 1 plus your eccentricity times your cosine of theta. And that will give you your radius with respect to, in this case, the sun. So your distance to the sun. And then all this is doing here is it's appending your radius times the cosine of your true anomaly plus your argument of periapsis. So what it's doing is saying, okay, well, if you are at 0 degrees in your orbit, you're at your periapsis. So your argument of periapsis is going to be some angle in the 2D plane. Say, for instance, your angle is, like, you're straight down in the 2D plane. You're 270 degrees. So in order to find your components of R, you have to take that true anomaly angle plus that argument of periapsis plus any true anomaly that you may have accumulated throughout your orbit. So as it moves around your plane, you need to also account for that true anomaly, as well as your argument of periapsis. So it adds the two. It takes the cosine and sine to find your x and y components, and then it appends it to your two lists, x vals and y vals, and then it increments t. And then these next two sections, or next three sections, are all, I guess, optional. The first two is one that I like to include. Basically, instead of just drawing the shape and then kind of iterating over itself and making no difference, it introduces a length to each of the propagations. So if we look back at the GIF here, we can see that there's a trailing behind. Like, obviously the leading edge here is the planet or the moon, and the tailing edge is where it falls off. So this is just an arbitrary number 50 of just, after 50 data points, start cutting off a tail. And then we have a moving segment which is actually really good to illustrate here. 2b Enki is a asteroid that goes between Mercury and I believe Jupiter, about. And you can see it's actually a very good demonstration of Kepler's third law of how as you are approaching your apoapsis, you move slower. So the length of this arc actually decreases because you're taking more time steps to sweep out the same amount of area. So your tail decreases as you get to the apoapsis. And as I can show when we run the simulation again for you, it'll increase around the sun. And then these two sections are what I'm currently just using as a work to try to see if I can manage to create a transfer orbit. So what I want this to do is to take a standard Earth-Mars Hohmann transfer, which requires a angle between Earth and Mars to be about 44 degrees of a lead. And then you can create a Hohmann transfer, which goes from the current altitude, the current radius of Earth to the future radius of Mars. And I'm not going to go into too much detail about this because a lot of the logic in here is still iffy, and I've been having some issues with the orbit plotting on the same graph as everything, like it's not quite showing up. So I still need to work on a workaround for that, so I'm not going to be showcasing that here. However, I believe it will appear in the legend. So then all this does is that once it iterates through everything and it pops out any long-standing values, all it does is that it prints out, or it gives us this config list. And then that goes back here into the new config list. So for animate in each frame, it runs through that function. And then all it's doing here is that it's just creating the plot, it's setting the background to black, and then for here, it takes each body in the config list, and it puts everything in the legend, and it gives it a color, and then it plots all of their X values and Y values that are currently in the list. This is also what I'm trying to figure out about the transfer orbit. I'm trying to figure out exactly where to fit this into the workflow. And this sets the limits for the graph for the X and Y direction. And this is aligned to make sure that we always get a box so that both are equal pixels on the screen. Because if you don't have this line, it'll take up like a proportional rectangle on your screen and then everything gets skewed. So just to make sure that everything appears correct. And then setting all the axes to white, adding epoch time, which is just the amount of time that's passed since like T0. And I have this in passing and Earth days. And then we just have our labels. And then going back here, that does the animation. And then it just basically just shows the plot. So that's my code rambling. And now I'm going to go ahead and give the demonstration. If it runs. Come on now, don't be shy. It appears it is quite shy. I'm going to go ahead and give it another shot here. What's interesting here is that I've been working on this on my laptop, which is surprisingly really low end, and this works just fine. And then I bring it over here to my Windows machine, and which has Python and everything installed in it, and for whatever reason the window decides not to show up. So I'm going to go ahead and try to give this a go and see if I can get it to show. Okay, looks like we got that running. So what this is doing is that it's obviously propagating through each of these orbits, and it's actually running surprisingly smoothly on this machine. It has about 16 gigabytes of RAM. Actually, I can pull it up here just to get an idea of what kind of specs we're working with. For about 4.5 gigahertz on the processor, 16 gigabytes of RAM, and this runs actually quite smoothly, given how it has to simulate every body. It has to do a numerical calculation to find the eccentric anomaly, and it has to run all these functions. So it actually runs quite smoothly. As we can see here with 2B Enki, the arc length rapidly increasing as we approach periapsis because the velocity is increasing. You can see this on a lot smaller of scale on other elliptical orbits, but I specifically picked this celestial body because of how elliptical it is. How eccentric it is. As we can see, the eccentricity for this orbit is 0.85 and change, compared to everything else, which really, Mercury appears the most eccentric at about 0.2. As we can see here on the bottom, these are just kind of vestigial entries from trying to create a transfer orbit. What this did is that it takes the first instance of Earth and Mars being, Mars leading Earth by 44 degrees relative to the Sun, and as soon as it does, it calculates the trajectory, it gives an eccentricity, and for some reason it's not quite able to graph. So that's a future step. As you can see here, we have Jupiter kind of, sitting around here at the far edge, at just about that 80,000 mark. 800 million kilometer mark. So, and we can see here this tiny blue dot is the Sun. I would like to try to make that larger if I can. But again, this is pretty preliminary of just trying to see if I can propagate these equations into the future. So as you can see, we've just approximated almost, a little over 3 years of Earth time. Sorry, wow, not even 3 years. Actually, quite a lot more than 3 years. Mental math's a little bit iffy, but as we can see, this runs quite well. So a few closing notes on what I obviously aim to improve on this project. Home and transfer, I would love to do. The goal of this is that whenever Mars and Earth have a 45-degree angle, I want to create another one of these orbit objects and just propagate it through its home and transfer, and then once it gets to Mars, I'll just delete it, and then it'll be good to go for the next one, just as a visual thing to show exactly how often home and transfers will happen at that optimal angle, just as a visual aid. The thing that I want to do is use SPICE, which is the JPL databank. That would be ideal so that I could get much more accurate ephemerae of each of the celestial bodies, because right now I'm basically just running off of a database that I scraped from Wikipedia. So while it is relatively accurate as far as accuracy, it's within maybe, within maybe 10,000 kilometers of accuracy on either end. So anything that could be a lot more up to date as far as its epoch, the better. But this works just fine as a proof of concept, I believe. Again, I feel like this is probably a pretty good demonstration of intermediate orbital mechanics, as this is just taking, I believe, 4 equations from my spaceflight mechanics class and just using that with my knowledge of Python to go ahead and create a program that, if anything, creates a pretty cool screensaver in my opinion. So with that, I'm going to close this little presentation. I will be continuing to post updates as I am working on this on my website and on my GitHub. I will be obviously regularly updating my GitHub as I do work on this project. And any other future projects that I do work on will also be updated on this website as well. If anybody who happens to be watching may have any input on how I may possibly optimize this mean to eccentric function, or how I may be able to implement spice, or really kind of any of the issues that I mentioned. Obviously, criticism is very appreciated, as I am just a junior in college who has relatively intermediate Python experience, as far as a student level of experience is concerned. So, thank you very much for sticking around and listening to my ramblings if you've made it this far, and I will see you later.